Use the information Appendix D to calculate the pH of a solution of 0.25 molar sodium formate and 0.1 molar formic acid. All right, so this is a common ion problem, right? So you have a whole bunch of the conjugate base of formic acid suppressing the ionization of this weak acid. So, when we used to solve for this, right, for every X amount of formic acid you're losing, you're making X amount of H plus ion, X amount of acetate. Well, X gets even more inconsequential as you put more and more formate in, right? It shifts the equilibrium back towards the formic acid. So X is super insignificant here. I don't have to think about the change in the concentration of formic acid or the change in formate. I can just plug these concentrations in and solve for X. So 0.1 times 1.8 times 10 to the minus 4, the Ka for formic acid, divided by 0.25 gives me X. Take the negative log and get the pH. So it's the same with B, a solution where you've got 0.51 molar pyridine and 0.45 molar pyranimium, Jesus, that's a tough one, chloride. What you've got here is a weak base and its conjugate acid. So I turned it around. I talked about the weak acid and its conjugate base. We could do it either way. You could do this as a Ka expression or a Kb expression. So if I wanted it as a Ka expression, I just take the Kb value for pyridine or pyridium or whatever it is, and divide into 10 to the minus 14 to get the Ka for the conjugate acid. So now I can do the same thing. I can ignore the change in the concentration of the weak acid, the amount you're adding to the conjugate base, solve for X, take the negative log and get the pH. So again, with this whole bunch of conjugate base in there, the pH is going up, right? You're suppressing the weak acid. Less of it's ionizing. All right, C, a solution made by combining 55 milliliters of 0.05 molar hydrofluoric acid and 125 milliliters of 0.1 molar sodium fluoride. So again, we've got, first thing, right? They give me milliliters in the molarity, right? So we have to figure out how many moles of fluoride ion have floating around in there, how many moles of hydrofluoric acid have floating around in there. Then if I divide by the new volume, right, if I add 55 milliliters to 125 milliliters, I get a new volume of 1.8 liters. I want moles per liter if I want concentration units. So plug these concentrations into law of mass action. Again, solve for X and get the H plus concentration. Now, looking at this, right, if I divide 1.8 by 1.8, I can ignore the volume here, right? I can just talk about the ratio of the moles when I have a common ion situation. So I can just plug moles into the Ka expression and solve for H and get the same answer as I would if I converted first to moles per liter. So I hope you understand that. Let's just go back one. Recognizing that this is the concentration, when I divide the concentration of the conjugate base by the concentration for the hydrofluoric acid, they have the same volume. So 0.18 milliliter liters divided by 0.18 liters cancels. So I can just plug moles into this Ka expression and solve for the H plus concentration. Get the pH. Now, A, B, and C. These are all common ion situations. And guys, when you have a weak acid and its conjugate base in high concentrations, this is called a buffer. So an alternate way of solving this problem is plugging into the Hasselbalch equation, right? We'll talk about the Hasselbalch equation in class, where it's just makes it easy sometimes. Just plug into this equation. They give it to you on the AP exam. If I know what the conjugate base concentration is and the weak acid concentration is, I can plug into this along with the negative log of the Ka and solve directly for what the pH is. So frankly, we're going to want to practice this. When we have a common ion situation, it's easier just to plug into the Hasselbalch equation. You can plug moles in or moles per liter and you'll get the same ratio. Calculate the percent ionization of a 0.125 molar lactic acid solution. Okay, so this is a straight Ka problem. For every X amount of lactic acid lost, you're making X amount of H plus ion, X amount of the conjugate base. Plug into the law of mass action and solve for X. All right. Percent ionization typically is taking the conjugate base concentration and dividing it by the conjugate acid concentration. Or I should say the original concentration of the acid, right? So how much did it ionize? How much did it break apart? So we take X and we divide it by my original concentration of lactic acid times 100. And that gives us percent ionization. Now we do the same problem, except this time we've got a conjugate base, right? We got a whole bunch of 0.0075 molar lactate floating around in there. So this is going to suppress the ionization of the lactic acid. So in this case, we're looking at the H plus concentration as to the percent ionization of this weak acid. The lactic acid is suppressing the ionization of the lactic acid, so X should be smaller. Right, so when I solve for X and divide it by the original concentration times 100, yeah, we see that we have a lower percent ionization with a common ion than we do with the lactic acid. Notice we didn't use the Hasselbalch equation for this one because you're not solving for the pH. Now you could have, I guess, in going backwards, take the base 10 of negative pH to get X, but it was easier just to plug in the Ka expression to solve. Solve for X, compare X to the original concentration. Explain why the mixture of acetic acid and sodium acetate can act as a buffer while hydrochloric acid and sodium chloride cannot. Well, a weak acid has the weaker the acid, the stronger the conjugate base. So when we talk about acetate, this is a significant base because acetic acid, was an acid that didn't really want to give an H. So you've made something that can take an H. Whereas with hydrochloric acid, right, the conjugate base of chloride ion, chloride is a non-base. It can't take an H. And sodium ion is just the cation that accompanies the hydroxide. So it has no hydrolytic value. So if you're going to make a buffer, you have to make it out of a weak acid and its conjugate base. So calculate the pH of a buffer where you've got 0.12 molar lactic acid in a 0.11 molar sodium lactate solution. So again, it's a common ion, right? So these are the concentrations of the weak acid and the conjugate base. We could plug these concentrations directly into the Hasselbalch equation and solve for what the pH is by taking the pKa and adding it to the log of the C base over the concentration of the acid. So plug into the Hasselbalch equation and solve for the pH. All right, calculate the pH of a buffer formed by mixing 85 milliliters of 0.13 molar lactic acid with 95 milliliters of 0.1 molar sodium lactate. All right, so the first thing we have to do is figure out how many moles of lactic acid and lactate we have. Now, I could divide by liters, right? 85 milliliters plus 95 milliliters gives me 180 milliliters, right? 0.18 liters to get molarity. And then take these concentrations and plug into the Hasselbalch equation. Solve for the pH that way. Or we could recognize that, again, we've got moles of lactic acid, moles of lactate, and we can, if we divide by liters, plugging into the Hasselbalch equation, those volumes cancel. So I don't actually have to, again, belaboring the point, convert back to moles per liter to plug into the Hasselbalch equation. I can just plug moles of lactic acid and lactate in and solve for the pH. So either way, it comes out the same. You're asked to prepare a buffer at a pH of 3, starting from 125 liters of 1 molar hydrofluoric acid and excess sodium fluoride. All right, what's the pH of hydrofluoric acid? What is the pH of the hydrofluoric acid prior to the sodium fluoride? All right, so A is just a Ka problem, right? So I'm starting with 1 molar hydrofluoric acid. I'm losing X of hydrofluoric acid, making X of fluoride ion and H plus ion. Take these equilibrium concentrations, recognizing that the original concentration of hydrofluoric acid isn't changing, and solve for X. Take the negative log, get the pH. B, how many grams, this is the new problem, how many grams of sodium fluoride should be added to prepare the buffer? Neglect the small volume change that occurs when sodium fluoride is added. All right, so they want us to make a buffer at a pH of 3, and they told us that we have 1.25 liters of the 1 molar hydrofluoric acid. All right, so again, liters times moles per liter gives me moles of hydrofluoric acid. I can plug moles directly into the Hasselbalch equation. And what I can solve for here is moles of fluoride ion, right? The pH is going to be 3. So I know what the pH is in this case. So negative log of a number is a number. Subtract that number from both sides. Take both sides of the base 10 to get rid of a log. And I can solve for what the moles of sodium fluoride would have to be. They wanted grams, so use molar mass to get to grams. So it's nice with the Hasselbalch equation, right? I can plug the pH in and figure out what kind of buffer I want to make depending on the pH I want to buffer at. (29). So here's another one, right? What is the ratio of hydrogen carbonate to carbonic acid in blood when we have a pH of 7.4? So that's my pH I'm getting to, right? So my pH is 7.4. What I want to solve for is what the ratio has to be of hydrogen carbonate to carbonate. So negative log of the Ka is the pKa. Subtract that from both sides. And then take both sides of the base 10 to get rid of log. And I solve for what the mole ratio's got to be. I need 10.8 moles of the hydrogen carbonate to 1 mole of the carbonic acid to get a buffer at a pH of 7.4. B, what's the ratio of the conjugate base to acid in an exhausted marathon runner whose whose blood pH is 7.1? All right, so again, we know what our pH is at 7.1. What we want to solve for is what the ratio of the hydrogen carbonate to carbonic acid's got to be. And we can do that. So 5.4 moles of hydrogen carbonate to 1 mole of carbonic acid if I want to get to a pH of 7.1.